Hi, and welcome back. As you saw, there are so many parameters the meta-profit model needs to estimate. Let's look at how these parameters are estimated using a Bayesian approach.
For both trends, linear and logistic, the key is to balance the flexibility of the model, that is, being able to fit the historical data closely, with the risk of overfitting, that is, fitting too closely to the historical noise and therefore making poor future predictions. This is where the Bayesian methods shine, as they allow the modeling of uncertainty and introduce regularization based on the prior distributions. The Bayesian method is used to estimate all parameters necessary for the linear and logistic segments. In forecasting models, the only information available is the historical data. Because the unknown parameter can take many values, it will necessarily be stochastic in nature and belong to a certain distribution, and the right parameter will be the most likely value for this distribution. The question then becomes which distribution this parameter will take. We can formulate this problem using the Bayes theorem by asking what is the probability of seeing theta given the available data. This is the formulation of the Bayes theorem for parameter estimation, in which each probability is a probability distribution rather than a single value. We want to understand the posterior distribution over the unknown parameter. This is what we want to know. We want to know about the parameters after we see the data. By applying the Bayesian theorem, we know this quantity to be equal to this formulation, with the P of theta is the prior distribution of the parameter theta. This represents our belief, what we know about theta before observing new data. P data given theta is the likelihood of the data given the parameter theta. It measures how well the model with parameter theta explains the observed data. P data is the marginal likelihood or evidence. It is the probability of the data under all possible values of data. In practice, it serves as a normalizing constant to ensure the posterior distribution is a valid probability distribution. It is defined as this integral, which is often intractable for complex models, which is why special methods are employed for its calculation. Before, I stated that P of theta is the prior distribution of the parameter theta. This represents our belief about theta before observing the data. What does it even mean? This is a key difference between a frequentist and a Bayesian approach to parameter estimation. Frequentists and Bayesians are two schools of thoughts about different approaches to the interpretation and application of probability and statistical inference. I will spend just a little time on this, but in our example, a frequentist approach would estimate the parameter theta as a single and fixed value, while a Bayesian as a probability distribution. Let's explain the difference with this example. Let's say you are ready to drive to your office and watching the traffic report. The probability of driving in wet and flooded roads is 50% in the three-state area in the USA. Driving on wet roads can be very dangerous, so you take a deep breath and leave early. Because this is the only information you have at that time, you prepare yourself for a long commute with traffic and difficult driving conditions. The probability of 50% is fixed in the frequentist school of thoughts and it will not change. You start to drive and you see this, a nice dry road and almost blue sky with no traffic in sight. Do you still believe the probability of wet roads in your area is 50%? As you receive new information, your belief of driving on wet roads with difficult driving conditions changes. You are more confident that the commute will be okay and nothing to worry about. This is the difference between a frequentist and a Bayesian approach. The difference between the two approaches extends to the way parameters are estimated. In a frequentist approach, an unknown parameter is estimated, and once estimated it becomes a single fixed value. In a Bayesian approach, parameters are random variables, that is, they are described by probability distributions. There is not a single fixed value, rather many different values that be realized with different probabilities. This is why the posterior distribution and the Bayesian estimation is a distribution and not a fixed value. And it is for this reason that a Bayesian approach is better equipped to handle uncertainty. It is for these reasons, for example, that Bayesians are quite critical of the traditional hypothesis testing based on a single and fixed p-value. Having said that, it is also fair to add that often the Bayesian results coincides with frequentist-based results, but offers more flexibility.
In this module, you saw how the Bayesian theorem is used for parameter estimation. This approach is at the core of the Bayesian approach, which is quite different from the frequentist approach of estimating a fixed value independently of the new knowledge acquired by the model. In the next learning module, you will learn how MetaProfit deals with this apparently impossible integral for estimating the posterior distribution. I will see you next.